I want to go over both parts of this problem to make sure everybody understands how the formulas work. So part 1 reads, determine how much energy in electron volts an absorbed photon must have at a minimum to free an electron that is in the 14th energy level around a hydrogen nucleus. Okay, so we're talking about the energy, so we're going to use this formula right here. So I need the Rydberg energy, which is 13.6 electron volts. 1 over, now I need the lower energy level. The lower one is 14, and I got to square that. And then the higher one, we're trying to free the electron, so that means the energy level is infinity. So infinity, and I got to square that. 1 divided by infinity is 0, and if I divide by 1 by infinity squared, that's obviously still going to be 0. So that's just 0, so this becomes 13.6 electron volts divided by 14 squared, and that's just 0.06939 electron volts. So there we go. Part 2, an electron drops from the 28th energy level to the 2nd energy level. Determine the wavelength of the emitted photon. Okay, so we're going to use this formula for that because we're interested in the wavelength. Important to note that it is 1 over the wavelength. And then I need the Rydberg constant. That's 1.097 times 10 to the 7th inverse meters. The lower energy level, it's the 2nd energy level, so 2, so 1 over 2 squared, minus the higher one is 28, so 1 over 28 squared. All right, so then just go ahead and plug this all into the calculator. And I get, oops, the wrong number. Hold on real quick. There we go. 2,728,507.653. This would be inverse meters. This is not the answer. We solved for 1 over the wavelength. We want the wavelength, so we need to take the reciprocal of both sides. And so when I take the reciprocal, I get 3.665 times 10 to the negative 7th meters, which, if you're expressing this in nanometers, is 366.5 nanometers. There you go.